Welcome, everyone. The Society of Petroleum Engineers Unmanned Systems Technical Section is pleased to present this virtual seminar, Insights into the Physical Phenomena that Influence Automatic Gain Loss Detection During Drilling Operations. My name is Jennifer, and I'm the facilitator. Please note that this call is being recorded and all lines are muted. If you need help at any time, simply send us a message in the chat box. Today's presentation will last up to 90 minutes and does include a Q&A section at the end. However, please feel free to queue up your questions for us at any point during the presentation. We do encourage you to get them in early. To send your questions, simply type it into the chat box in the lower left corner of your screen, and then be sure to click on the send button. There are poll questions throughout the presentation. When a poll question appears on your screen, simply click on your screen in the box next to your answer choice. Now I am pleased to introduce our moderator. Dr. Andrea Kusters did a PhD in fluid flow at the University of Cambridge. She then joined the drilling technology team at BP, where she focused on real-time data and drilling optimization. She recently went traveling for a year and is looking after the webinars for the SPE Drilling Advisory Committee. Andrea, welcome.
Thank you, Jennifer. I would also like to thank the SPE Foundation for sponsoring this web event. And now I'm pleased to welcome our speaker. Mr. Erik Cailleux is the Chief Scientist at IRIS in Norway. After a 20-year career in the oil and gas industry, specializing in drilling and well software solutions, he joined IRIS in 2004. He holds a master's degree in civil engineering from the École nationale des travaux publics de l'État, France, and a master's degree in software engineering from the University of Nice, also France. Welcome, Erik, and over to you.
Thank you very much, Andrea, and thank you everyone to attend this webinar. So the topic of my talk will be about gain loss detection and the problem associated with the automatization of this detection. The talk will be presented with this outline where we start with a short introduction, just setting the scene for the problem. And then I will review some of the gain loss classical indicators. I will focus afterward on the measurement of the flow rate out of the well, especially accounting for what happens inside the well. And then I will have some review of what happens when we have pressurized MPD operations. Next, I will look at normal variations of active volumes, which can make it more difficult actually to detect abnormal situations like gain and loss. And before taking the conclusions, I will go through two examples, one with kick detection during connection time in a conventional drilling operation, and the second one, which is more not standard, which is how to take drawdown test during an MPD operation. So let's start with the introduction. Basically, what we can see here on this graph, which is taken from a real operation in the North Sea, is that at the connection time, we have the active volume, which starts to deviate from normal behavior. As we can see, the blue line is the actual volume, which is measured in the pit, and the green line is modeled the value that should have happened. And as we can see, when we start the pump here, the active volume should have decreased, and actually the real volume started to continue to increase. In this particular context, the team was not prepared to any gain, as there was no obvious indicators that things were not normal. There was neither connection gas nor drilling breaks just prior to this connection. And because of the unpreparedness, actually it took a lot of time before they decided to shut in and close the well. So it's a bit not so good that actually it takes so much time actually to stop such a situation. The second example is also a real operation. This time the context is quite different. We have been drilling, and we have a normal situation by the fact that we have pack-offs. As we can see on this side, on the SPP, we have multiple pack-offs which are repeating themselves. The driller reduces the flow rate, as you can see here, when each time he got the pack-off. And at the same time, he has problems with over-torques and overpulls and set-down weight. So he has a very difficult situation. And because he's busy with manipulating the string and the pump to get out of this particular situation, he oversees the situation which happens when he is obliged to shut down completely the pump here because of a more intense pack-off situation. That actually, just after he stopped the flow rate on the pump, actually the active volume started to increase more and more. Not very fast, but they started to increase. And basically, it took a lot of time before actually the team reacted to the situation, because they were busy with this stuck pipe back-off situation, and it's only more than 2 hours later than actually they shut in the well. Those two examples are maybe quite extreme, but that's just to set up the scene of the problem of gain loss detection and detections seriously and to take timely decisions for stopping such abnormal situation. So therefore there is a good interest actually to try to automate the detection of gain and loss situations so that we try to help the drilling team during drilling operations to warn them in a reasonable time fashion so that they can take these decisions in a better way. On the other hand, the problem with automatic gain loss detection is that if we have too many false positives or negatives, then people will not trust into this automatic detection methods. So we will need to decrease the number of false positive and negative to really minimum as possible. So the problem is that actually with gain loss detection there are many different physical phenomena which influence the parameters which are usually used to detect whether we have an abnormal flow from the well, and therefore we will review through this presentation some of those physical phenomena and how to try to deal with them. No, just to make a short break, we will have a poll question, and basically as just a starter, so I will ask you to answer whether you are coming from North America, South America, Europe, Africa, Middle East, Northern Asia, Southeast Asia, or Oceania, just to see what is the distribution of geographically of the audience. I see that there is a larger number of people from North America and also a good number of people from Europe. Okay, so it's good. Then we will continue, and basically I will start with the basics. What are those typical gain loss indicators that we usually utilize? Let's going back first and look at what actually means that we have an abnormal gain. And basically, when we are drilling and we are an up-node section, so if the downhole pressure gets below the pore pressure, so we may have formation fluid which can enter the borehole, and that will create an additional flow, and that means that actually out of the well, so we will have a flow which is larger than what it should have been. That is definitively what needs to be detected to detect what we call a gain. Similarly, if we have a downhole pressure which is larger than the fracturing pressure, though we may start to induce fractures into the rock, and that means that drilling fluid can go into the formation and we will get a loss, which means that the flow rate out of the well will be lower than what it should have been because we have losses to the formation, and that would be a loss condition. So here is an example of a lossless situation. Since in the introduction I focused on the gains. This is a particular an actual operation where we have a constant flow rate, as you can see here. We are moving the block upward, and we have a relatively constant pressure. But nevertheless, at some point in time, actually, so the flow rate measured with the flow paddle, we will return back to what the role of this flow paddle was constant, and then it starts to drop. And that means that actually we have got a situation where we've got losses to the formation. Now, what are the typical indicators for these gain-loss situations? Of course, it has to do with the flow rate out of the well, and there are in a way different methods to detect that the flow rate out of the well is abnormal. The usual one, which is used everywhere, is to look at the active volume and see if there is any abnormal variations of the active volume. This is relatively easy things to do when we have steady state conditions, like the loss condition that I presented just earlier. Everything was steady, the flow rate was steady, there is a very small speed about the three-string movement, so that would be quite easy to detect on the active volume that we have a loss situation. It is quite more complicated actually to detect abnormal variations of active volumes during transient periods, and what is usually done is to use fingerprintings to check with similar transient periods whether we have the same behavior or if the behavior is starting to deviate. Later on we will look into the challenges in using this fingerprinting. And then the last point is that actually it is quite often that actually people are the med engineer is giving orders to do some management into of the fluid into the pit, and therefore we will put more barite and we will put more base oil and brine, and that will change the volume, which is not a non-normal situation. It's just the way the operation is going on. So that will disturb also the picture for active volume based gain-loss detection. Another method is the so-called delta flow, which is basically just to make sure that the flow rate in and the flow rate out are equal. This delta flow method is basically based on the fact that within steady state conditions, so that should be okay. This is not really easy to use because flow rate in equal flow rate out is curve of the fluid in and the temperature of the fluid out are equal, because if they are not equal, actually there is differences in density, so the fluid in and the fluid out, the flow rate in and the flow rate out will not be equal, even though the flow rate is constant. And it is necessitating a reliable measurement of the flow rate out, which is not that simple. The classical way to have an estimation of the flow rate out is a flow paddle. And we'll come back in a few minutes into the challenges associated with interpreting flow rates coming from flow paddle measurements. The other thing is that actually if we want to compare flow rate in with flow rate out, we also need to have a flow rate in which is measured precisely enough. And in most cases the flow rate in is measured based on pump rates, and pump rates needs to be converted into flow rates by using an efficiency of the pump itself, and actually this efficiency is not something which is constant. It is depending on actually many different parameters, including both the pressure inside the cylinders and the viscosity and density of the fluid. So it's not that's certain that we have a good measurement of the flow rating as well. A variation of the delta flow method is actually to look at the pressure at the standpipe and the pressure in the at the outlet in steady state conditions. This is something which is easier to measure. That is therefore can give actually good results. Nevertheless, to use the pressure on the outlet, so we need. This is quite feasible if we have a back pressure MPD operation, because we have a well which is closed by the rotating control device. If we are working with conventional drilling condition, then we need to create a small pressure drop so that we can measure the effect of the change of flow rate on the pressure that is measured below this restriction. And having too much pressure drop can mean actually that we have some problems with the levels into the annulus. So it's not necessary that we want to do that as well. And then another method is the so-called processed flow rate out. Basically, it requires a good measurement of the flow rate out, like with the Coris flow meter that exists on some modern rigs. That you have the Coris flow meter, which is installed on the flow rate out of the well, and it requires also good description of the borehole, because you will need to manage actually what should happen inside the well while you are pumping, and how this correlates with the flow rate out that you are measuring. All in all, what is important here is to see that in steady state conditions we have several methods which can be quite reliable. The biggest challenges are actually when we have transient periods, where actually there are many different things which are happening, which are disturbing the picture for detecting the gain and loss. So that's what we will review now through the before doing this review, so I'll go to another poll question, and I would like to ask you, when do you get most of your kick situations? Is that while you are drilling with constant parameters in steady state conditions? So you can start to click on the checkboxes if you want to answer, or you can. Is it while you are taking connections, or is it while you are pulling out of hole after drilling, or is it during wireline operations or cement jobs, or is it also when you are leaving the well static for a long time? So I see that actually there are many people say that they have problems while pulling out of hole. That's typical because of the swabbing. Quite a few also indicating during connection time, and a few also on while the drilling parameters are constant. So thank you for this input. Then I will continue and look at the measurement of the flow rate out from an annulus, and is the flow paddle. Here is a picture of one flow paddle, and basically it's a very simple tool, but it doesn't give directly a flow rate. That just gives us in a way the level into a return flow line. So how do we connect this level into the flow line, which is expressed as a percentage, and the flow rate? And if I take this example from an operation, if I take the flow rate in as the abscissa and the paddle percentage on the ordinate for a particular section which has been drilled here, we can see that basically there is a challenge. Is that actually for the same flow rate, there was some markers there, but for the same flow rate, I will get a whole range of different flow paddles compared to the flow rate in. Even though the flow rate in is constant, so I get different values for the flow paddle percentage. So that's that's giving a problem because we can't convert directly the flow paddle, the flow paddle percentage into a flow rate out typically. Note also that with this particular flow paddle in this operation, it doesn't indicate anything as a percentage before the flow rate is above 500 liters per minute. So so the problem is that actually we get into situations where the flow rating may be constant, and then yet the flow rate out is still changing. And that is illustrated by this picture that I have here. It's drilling in 6-inch. It's a relatively long well. We have 8,000 meters in bit depth. And as you can see here, so we have a steady flow rate in here at that time. And yet the pump pressure continues to increase. We don't detect anything in terms of the flow paddle. It's because of this 500 liters per minute before we can detect something. But if I calculate which is a green line, when do I get actually a steady flow rate out? Actually, it takes a lot of time. It's delayed by several minutes before I will get a steady flow rate out. And that's due to the compressibility of fluid. We have a very large volume of fluid into this well, and we have a large pressure gradient while we are pumping. And that causes actually an imbalance that needs to be compensated by putting more fluid into the well to account for this compressibility. And that is reflected also on the pump pressure, which will take actually almost 4-5-6 minutes before it's stabilized, and that is a consequence of this compressibility of the fluid. So that means that, and when we look at the flow paddle here, it continues to increase from 0 to this 7-8% much after we have finished being with a steady state flow. And that is causing these values which are repetitively or different flow paddles opening for the same flow rate. So it would be much better if we compare the flow paddle percentage. Yeah, okay, sorry. Before I do that, I will show you an animation. I hope I can. There. Here is the animation. We have that illustrate for this particular well how much time it takes actually before we get the flow rate out of the other well. So I see that I can't show with my cursor what is happening there, but it's only know that actually the flow rate, the blue curve shows the flow rate out of the well much later after the flow rate in has been stabilized. And that is an illustration of the time that it may take for long wells with large volumes and large pressure gradients to get a stable flow rate out. And as you can see here, it continues to be lower than the flow rate in for many minutes because at the same time the standby pressure is increasing, and we need to put more and more fluid into the well to compensate for the compressibility of the fluid. So let's move on and look at the how it would be better to compare this flow paddle opening, and that would be to compare with the flow rate, estimated flow rate out of the well by accounting for this compressibility. And that, as I showed earlier, that is this green curve that I'm showing here. And if I put into the abscissa for this graph the estimated flow rate out, I obtain a different picture than earlier. Well, actually, obtain actually two kind of curves. You can see there that there is something strange. Actually, I've for the same flow rate out, estimated flow rate out, I got two set of points which can fit with that, and that is quite surprising. So are we doing something wrong here? Well, actually not. The reason for that is that actually we have a situation where we have a change of rheology during this operation, And basically what happened is that actually when I colorize the measurements of the flow paddle compared to the flow rate, estimated flow rate out in green for the one rheology and in red with the other rheology, I see that actually there are different curves which are represented there. And this is due to the fact that actually it's not only a question of compressibility, it's also a question of pressure losses, but also on the accumulation of fluid into the flow line. And as we can see here with the schematic view of the return flow line, the level that we will get into the flow line will depend on the effective viscosity of the fluid. There is also something else which comes into the picture. It is that actually the pressure losses into the areas will be different if we change the rheology. And that is what is illustrated here with these graphs. Comparing two drastically different type of rheology, one which has very low viscosity, which is the green curves, and one which has a more standard viscosity, which is the yellow curve. And if we look at the estimated flow rate out, which are shown here on the first part of this graph, we will have, especially when we start and when we stop the pump, quite a big difference in terms of the response between the low viscosity and the high viscosity fluid. The pump pressure will be different. The volume will be different, as you can see here, quite a few difference there. And that's because also the bottom hole pressure are different because of the pressure losses through the annulus. So all this will influence actually the readings that you will get into the flow paddle. So it's not only a question of compressibility, the viscosity of the fluid and the rheological properties also play a very important role, because that will have an impact on the pressure loss that we will have inside the whole system. Now, as I mentioned earlier, the flow rating is quite important, and there is something that we need also to understand, is that often the flow rating, as it is based by measuring the pump rate, may be out of sync. Because at low flow rate, it may take several seconds or several tenths of seconds before we get 2 strokes. And when the pump rate is measured with a stroke counter, we may end up into this particular situation that you can see here on this graph, where actually we see a pump pressure increasing at that time, while actually the pump rate or the flow rate reported by the drain control system, and it takes actually in this particular case 25 seconds before we start to see actually the pump rate or the flow rate starting to increase, while actually we're already reaching something like 40 bars. And that's because actually it takes time just to count the number of strokes when we are pumping at very low flow rate. So that will also be have an impact when we calculate our estimated flow rate out, if we get delays in the actual flow rate in, which is pumped into the well. That is also something also to account for any methods which try to detect abnormal variations of the flow rate out. Now, let's move on to a different context where we have pressurized MPD operations. In this particular context, so we have a rotating control device, and we have a back pressure pump which can actually circulate through an MPD choke, and quite often we have a Coris flow meter just after the MPD choke, so that we can measure the flow rate out. And that is quite an ideal situation, because then we have precise measurements of the flow rate out as well. And that's definitively much more reliable than a flow paddle. Nevertheless, there are some things that we need to also to account for that. As it is illustrated here, when we change the opening of the MPD choke, as it is shown here, we will see some differences in the flow rate measured between the chorus flow meter, which is placed behind the MPD choke, and the one which is in the inlet. And the reason for that is that actually, because of the compressibility, we are changing the pressure when we change the opening of the MPD choke, and therefore we have also again a necessity to pump some more volume or less volume to compensate for the change of pressure that we have inside the hole, and that is of course linked to this variation of pressure that we have there. So some variations may have actually during also pressurized MPD operations, even with good precision instrumentation. We need also to account for this compressibility when we are changing the settings of the MPD choke setup. Here is an illustration of the difference that we can notice also between the chorus flow meter, which is placed before the back pressure pump, and the chorus flow meter, which is placed after the MPD choke. And as we can see here also, we have some variation there. It's not very large, but which comes from that the whole system is actually being compressed and responds to the change of flow rate that we have into the system. So interpretation of the flow rate out has also to consider the whole well, and not only what is happening in the inlet and the outlet of the system, hydraulic system. Chorus flow meters can also be used in conventional drilling, yet the annulus is not sealed, so it's quite important that actually the chorus flow meter will create as little pressure drop as possible, because if it has too much pressure drops, then we may have an overflow at the top of the annulus. So that necessitates to have chorus flow meters which are of large dimensions to create as less possible pressure drop as possible, and that means relatively substantial footprints. So modern rigs can have chorus flow meters placed on the flow rate out of the well when they are actually a good place at the design stage of the rig to put the chorus flow meter. It's more challenging actually to put the chorus flow meter on conventional drilling when it has not been designed from before, because it needs to be set in the right way to avoid accumulation of cuttings into the chorus flow meter. Otherwise, we will need also to spend quite some time to flush the chorus flow meter to remove the cuttings each time there are accumulations into the instrument. So chorus flow meters for conventional drilling is possible. It's best actually when everything is designed for that. Otherwise, it's more complicated. Now let's look at the other topic, which is the active volume variations, looking at the volume into the pit. So basically, when we are drilling, the first thing that we need to notice is that we are increasing the depth of the well, okay? And by that we produce cuttings, and those cuttings are being transported. So actually, at the really start, when we start drilling, so we enlarge the length of the well, we produce cuttings, and we put more steel into the well. And what that would mean in practice is actually, if we look at the mass balance, that means that the pit volume will increase, because actually we are putting more material into the borehole. It's only when we have the cuttings coming to the surface and being separated at the shakers that actually the pit volume will start to decrease. So there is a long delay between the time that we have drilled or enlarged the whole depth, and we get actually a decrease of the volume due to the cuttings being removed at the surface. And that needs to be accounted for when we are trying to estimate any gain-loss detections and the impact of the cuttings transport itself and the change of volume that we are creating into the wellbore. Here is an illustration of what happens while we are drilling. The red dashed line is the actual active pit volume. It's a relative value. It's not the absolute value, but it's a relative value. And here the green curve on the right-hand side just shows the estimated cuttings flow rate based on some cuttings transport model. And as we can see, this cuttings flow rate is moving up and down and varying. And actually we can see that the active volume is following quite well actually those predicted values for the cuttings coming to the surface. This rainbow information there, that's the expected variations of the active volume based on this cuttings flow rate out of the well. Now there is a bound of different volumes, which is expressed here from bluish to reddish, and the reason for that is that there is always some mud sticking around the cuttings, so we will not have only to compensate for the particles which are removed, but also for the mud which is sticking around the particles which are removed. So that gives some uncertainty on really how much the volume will change while we are separating the cuttings from the mud. Because if we have a lot of muds sticking around the cuttings, then we will lose more than if we have very little muds sticking around the cuttings. And that depends very much on the size of the particles. But yet we can estimate those variations and estimate how much cuttings are coming to the surface. The other thing which happens with the active volume is that each time we change the flow rate, well, there will be variations of the active volume. As we can see here, we have a certain flow rate, constant flow rate, and we have an active volume here, which this time this is an absolute value. And then at some point in time, we reduce the flow rate, and as a consequence of that, actually the active volume increases. And that's just a few minutes later, so the flow rate is increased again, not exactly at the same value as originally, and the active volume decrease again. And actually you can notice that the final value that we have here is not the same as the initial value that we have here. Now, of course, you would say that this is because of the compressibility of the fluid. We have changed the pressure losses into the well, and that is causing this difference there. And that's one part of the answer to this variation of the active volume. The second part of the answer is related to what happens with the fluid which return into the flow lines and the shakers and the treatment pits before it goes back to the active pit. Basically, when we have a certain flow rate, there will be some retention of fluid through this return flow hydraulic network. And when we increase the flow rate, there will be more mud retained into this whole return setup. If the flow rate is lower, then the amount of mud which is retained into the system will be less. And that's the second source of variations for the active volume when we are actually changing the flow rate. So when we start the pump, so basically we will have accumulations of mud which will be retained into the return channel installations. And when we stop the pump, then actually all this mud which was accumulated into the return system will flow back into the pit, creating an additional volume which goes back to the pit. So here I will have an animation showing what happens when we start and stop the pump. So the pump has been stopped. The flow rate is zero. As you can see, the pump pressure is zero. Now it's starting. The pump is starting, and then we see here on this track here what happens with the active flow rate, active volume. We see that when we stop the pump, the active volume is increasing, and when the pump will start, actually the active volume is decreasing. And you can see also that if we model what happens into this return flow installation system, the green curve, which is the model values for the active volume, can compare very well with the values which has been actually recorded for this particular stop and start of the pump. So that's quite advantageous actually to have this. Now you can ask yourself, what is the proportion of this compressibility of the mud inside the hole in these variations, natural variations of the active pit, and compared to the accumulation of mud or the retention of mud into the return flow system after the outlet of the well. Here I have some illustrations for a particular well from the North Sea, with the 4 different sections. Here that will be only for 2 sections in this particular well. The first one is a 17.5 section, and the second one is a 16 sections. And for this particular stop and start of the mud pump, we can see that the active volume totally is actually changing by 5 cubic meters. Here on this curve you can see the modeled flow rate out, or the modeled flow rate to the pit after the return channel effect, and the yellow curve is the modeled flow rate out of the well at the outlet of the well. So the difference is the impact of the retention of mud into the return channel installation. And as we can see in this 17.5 section, so basically we have 40% of this volume, about 2 cubic meters in that particular case, which is coming from the compressibility into the well, and we have 60%, that means 3 cubic meters, which is coming from the retention of fluid into the return channel installation. This is quite different when we look at the 6-inch stop and start of the pump. In that particular case, it's almost impossible to see in this chart the difference between the flow rate out from the well, from the model flow rate out to the pit. That's because there is very little retention into the return channel installation. In practice, that means there is almost 90% of this less than 2 cubic meters variations that we have when we stop and start the pump, which is coming from the compressibility of the fluid into the wellbore, and only 10% which is coming from the retention into the return channel installation. So there is a big variations of these different impacts, different phenomenon for different type of hole size and lengths, and also of course the rheological behavior of the mud also influence quite a lot, as it will have an impact on the pressure losses that you will get into the well. Now, as I mentioned earlier, so it is very classical to look at when we have a stop and start of the pump during connection, and how the active volume is changing, and to try to do some fingerprinting. I'm taking 5 consecutive stop and start of the pump for the 17.5 section that's the 20-quarter section of this particular well. And the blue curve is the actual active volume variation that we have during the stop and start. Here we have the flow rate variation. So initially we start at 3,000 liters per minute, and we have a stop, and then we start back to 3,000 liters per minute, and we got an increase of the active volume by about 4 cubic meters. And then for the connection number 22, so we got another active volume. And this active volume is changing quite differently this time. Because actually we have a much longer connection time, and also we have a quite difference. Also, is that we were stopping from 3,000 liters per minute here, and we start the pump at almost 4,000 liters per minute. So that's also have an influence. And if we look at the curve itself, so we may think that maybe we are starting to getting losses. Especially if we do fingerprinting compared to previous pumps stop and start. So basically, it's quite difficult actually to match the two curves. So the next connection is again different, and we've got a situation where actually, because we didn't get a good survey, we need to restart the pump to cycle the MWT and to resend the directional survey, and that gives also a different look at the active volume because of that. Next connection is also again different. With some ways it's similar to the connection 22, because we stop from 3,000 liters per minute and we go back to 4,000 liters per minute. But the time is slightly different. The duration of the connection is slightly different from the connection 22. And then the next connection 25 is starting from a different flow rate and ending to a different flow rate. So that doesn't give the same value either. So this fingerprinting can be quite challenging actually to get things sorted out. But if we use a modeling of what is happening inside the borehole with the compressibility, and if we use also the modeling of the return channels, we get this type of picture where the green dashed line is showing actually the model values from the effect of compressibility into the borehole and the return channel. And we can compare with, regardless of different changes that we do, the duration of the connections, how this compare to the actual volume change that we have there. And if we look at those 5 connections there, we can see that actually we have almost systematically detection of losses. And actually there is losses in this well, not inside the well, but at the shaker, because there is overflow over the shakers. So this loss detection is actually quite real. Now, how those stop and start pump looks for different sections. Here I've summed up all the different stop and start for this particular well I was using as an example, for the 17.5 section, for the 12-quarter section, for the 8.5 section, and for the 6-inch section. And you can see you can have a bunch of different variations there, because any variations that you do in terms of flow rate and durations will have an impact on these active volume variations that you get there. So to detect losses or gains with this, it can be relatively challenging. I want also to illustrate another problem which is related to these active volume variations during stop and start. Here is a sequence of different stop and start. We are at connection 151, 52, 153, and so on and so forth to 159. And this graph on the right-hand side shows the active volume as it changes when we stop the pump. And I've colorized from red to green these different connections, and we see that it follows the same slope and basically the same top value there, because we use almost the same flow rate. But actually, we have a big difference with the last one, with the 159. And the reason for this big difference is that actually, I'm not sure if you see that, because in the original graph there was some curve showing what happens with the with the flow rate, but on my view, actually, I can't see the flow rate. But actually, between 156 and 159, so what is happening here is that we do hole cleaning, and because we do hole cleaning, actually, we are not producing any more cuttings, and actually, the cuttings which were accumulated on the low side of the return flow lines are getting also eroded during this period. And because of this change of the cuttings inside the return flow line, then the return flow line doesn't respond the same way. And that gives actually a different way of for this flow back from the well and the return channel when we stop the pump in the connection time 159. So that shows that actually this also needs to be accounting for what can be disturbing the picture in terms of cuttings accumulations into the return flow line. So let's have a very quick break and having a poll question. So I'd like you to answer, and you can just select these different checkbox. What is your particular ways of monitoring kicks or to do kick detections? Is it based on human monitoring, flow paddles? Do you use Coris flow meters? Do you have active volume monitoring, or do you have automatic gain loss detection? I see that someone is saying that they have active automatic gain loss detection, and then we have someone looking at the flow paddle. Is there any other practices for the audience? Yes, so not that many answers, so not sure we can draw very much statistic out of that when we have only 3 answers. So I'll just carry on with the presentation. So I go to the first example. This is a situation where we are drilling with a 9.5 bit and with a 10.75 underreamer. In this particular situation, there is no connection loss prior to the event. We have stopped the pump, and the blue curve here shows the active volume. The green curve shows the calculated volume as it should be happening. As you can see here, from that point in time, the calculation indicates that actually the active volume should flatten out, while actually the volume continues to increase. The pump are started at that time, and of course the calculations accounting for the pressure losses and the compressibility and the return flow into the channels says, well, you should have off the volume. And actually, this is just decreasing slightly. The increase, or the increase is not that as quickly for the volume there. So we can see that there is an abnormal behavior in that particular case, which can be detected relatively quickly about this situation where we have a gain at the connection time. So what I want to show here, and I here have a blown-up version of this particular thing, and we can see how the blue curves continue to increase, while actually the model versions actually say that it should flatten out. What was interesting actually in this particular case is that actually some time ago, before this connection, while they were drilling, between 25 meters and 15 meters of the block position. So basically something strange happened. If you remember what I presented here with the expected cuttings flow rate, which is a green curve here on the right-hand side variations, and the blue curve here being the actual volume being recorded. So basically what we got in this particular situation, while we were drilling the middle of the stand, is actually the pit volume started to increase slightly, just half a cubic meter. But that was not following what was expected there. Could be very hard to detect if you were not comparing that compared to what was supposed to happen with the cuttings transport itself, where we should have had a period where we had a decreasing level and followed by another period with a decreasing level. And actually what could be suspected here is that we start to get actually some gas going into the well, which increase slightly the volume. But this amount of gas is quite small, and also it dissolves into the oil phase of this oil-based bed, and therefore it doesn't increase very much in terms of volumes, and that masking quite well actually this gain that we are having here. So that's also another thing that can be done is when we have good control of the variations of volumes which would have happened compared to cuttings transport and also temperature variations that I didn't focus in this presentation but which are also important. You can also detect on impact on the possible gains and loss during the training operation. Just another poll question, quickly. How often do you experience kicks in your operations? Is it every well or every second well? That's answer A. Or answer B is up to every 5 wells. Or C is every 10 wells. Answer D is every 50 wells. Or E every 50, more than every 50 wells that you got a kick. Any input from you guys? So I see that there are several, so 3 persons answering something between 6 and 10, and then less than 50, and a few which are even less than 50, of course. So yeah, well, it's quite interesting to see that there are actually people having kicks so often than every 10 wells. Yeah. So it's very, very important topic. So let's go to the next the example. This is a very special example because it's during a managed pressure drilling operation. And this is not really a kick situation. This is actually a very particular way of testing the proximity of the downhole pressure to the pore pressure gradient itself, as it is a very narrow well. So the way it is done is basically through this MPD operation. So what we do is we make sure that we want to keep ourselves, our downhole ECD, between the frac pressure gradient and the pore pressure gradient. And to be sure that we are far enough from the pore pressure gradient, we want to do a particular test, which is called a draw-on test, to see when we start to get gas coming into the well. And this is done by reducing the setting of the back pressure MPD choke by 1 bar for 10 minutes, and just see whether we start to have some gains or not. And if we don't get the gains, then we reduce by 2 bars, and we carry on until we see things happening on the for the gain. So here, what happened during this first drawdown test, which was done in this particular well? We changed the settings of the choke, opening slightly more the choke opening, and that means that actually from the predictability measurements we have a reduction of the downhole pressure. And if we look at the core-release flow meter, enlarge here the picture, the green curve is what was expected by our calculations, and the blue curve is what is measured. You may see a slight difference, but it's very, very minimal. It's actually a larger difference when you look at the active volume variation there, because the active volume is a cumulative function, so it's the integral of the flow rate. So there you will see that actually we were expecting a decrease of the active volume because of thermal effects actually in that particular case, because we are circulating, we are drilling, and we have less pressure losses, so we are cooling down the well, and therefore there is a decrease of temperature, which means an increase of density and therefore decrease of volume. And we can see here that the model says, well, there is actually a behavior which is slightly different than expected. Nevertheless, so there was taken a second drawdown test, and what we can see here is that we increase even more the actual coupling this time, and the downward pressure decrease even more, and of course this starts to get visible on the Corys flow meter. We get a slightly larger flow rate out than expected, the green curve, and on the active volume we see something which is slightly increasing, but compared to the green curve, which is accounting for the temperature effects, actually we see a relatively visible increase in volume compared to expected values. If you didn't have the green curve, that would be harder actually to see that there was actually an increase of pit volume. Is it correct? That's of course a question. And if we wait long enough so that we get actually this mud which was exposed to potentially some gas during this first drawdown test, we see that the gas readings actually are showing something when the mud is coming to the surface, already for the first drawdown test. So our expectations that actually we were already with 1 bar close to the pore pressure gradient was quite correct. And it's even more obvious actually with the second drawdown test, where we get a much larger peak of gas later on. So we can confirm actually that the differences between what we detected of the flow rate out and the active volume compared to the model's values were quite correct for this particular case. So now I've reached the conclusion of my presentation. What I wanted to highlight is the importance of transient periods for detection of gain and loss. It is quite challenging to do this. We need to account for the compressibility of the mud, and therefore this compressibility is fairly affected by the pressure losses that will happen into the system, and therefore the flow rate and the rheological behavior of the mud. We need also to account for some thermal exchange, as I tried to illustrate with the last example, even though I didn't spend too much time during the previous part of the presentation, as it will have an influence on the mud density and therefore the total volume that we will get there. We need also to account for the transport of cuttings and the separations, as it will actually create natural variations of peak volumes that should not be, which will disturb the baseline for comparisons for detection of gain and loss. And we need also to account for all those transient effects that we have, accelerations and inertial thing that we have while we are starting and stopping the pump. And the return flow line from the outlet of the well to the pit volume are also playing an important role for the retention of mud, which will also influence the active volume that we have there. It will not influence the flow rate out if it's measured very close to the outlet of the well, but that will influence definitely the active pit volume. What I wanted to say also is that it is possible to do some modeling. It's not that requires some tuning of the models, but if we have the good tuned models and precise enough, so actually we can reproduce all those effects, and that gives a much better baseline actually to compare and detect gain and loss in complex situations. So with that, I would like to thank you for your attention, and hope that you will have some questions, and return to Jennifer. So if you want to
Great. Thank you very much, Eric. It is officially Q&A time, so if you have a question, please go ahead and type it in the chat box now. Once you do, be sure to click on the send button so that we get it. I know we've already had a few come in, so Andrea, I'll turn it over to you.
Yeah, thank you. Thanks a lot, Eric. So the first question we've got in here is, what model do you use to simulate two-phase flow?
Well, actually, we don't need to model two-phase flow when we are doing this type of calculations, because we are not accounting for the amount of gas which is coming there. We are just accounting for the compressibility and the pressure losses which are happening into the well. That would be necessary to use two-phase flow if we wanted to estimate the circulation out of the cake. But as the basis here is to detect actually an abnormal evolution of the flow rate out of the well, so it is not necessary to use two-phase flow.
Next question, do you consider fracture ballooning?
Yeah, we don't consider ballooning. In a way, ballooning will come as an additional effect which will superimpose to our predictions. Most of those variations that I've shown here can very well be explained by just the compressibility of the mud and the retention into the flow line. And of course, if there is some ballooning, that will look like some small gain and some small losses each time you start and stop the pump. But you don't need to go to use the ballooning to explain those variations, unless they do exist. So that will be detected as ballooning, or it will be detected as small gain and loss variations, which compensate each other. Yes?
And once you detect the gains and losses, is there an easy way to determine what dysfunction it could have come from?
Not really. That is good. That is a really good next topic in a way. The only thing which is done there is just to detect that there is an abnormal gain or an abnormal loss. But then you may have many different other reasons why you are observing these things. That could be, as I mentioned earlier during the examples, that you have losses at the shakers because of overflow. That may be that you have a leakage somewhere into the hydraulic system, or simply that people is adding more fluid into the pit. There you may have an indication if you compare both the flow paddle level and the active volume. So if you compare the two sources of information, so you may have some information to distinguish whether it is after the well or after the outlet of the well, or if it is inside the well. So, but so far we are not focusing on this. We just try to predict what should be the flow rate out of the well and what should be the volume change into the pit.
In the example, I think it was an example near the beginning, it took 40 minutes to detect the kick. Questions, was this also related to formation behavior, gas regression given as an example?
No, well, I don't want to enter the particular case. That was just an illustration that in a situation where people are not prepared, it may take some time to take a decision, even though there was something happening which was very serious. That's the kind of extreme case, and I don't want to go into the details of the case.
Sort of another question on the cuttings transport. What are your views on the best method to calculate carrying capacity index?
Well, we don't calculate the carrying capacity index. Actually, we try to track where the cuttings are at any time. So it's a transient cuttings transport model, which says, okay, here we have a cuttings which is a certain amount of cuttings which is produced by the bit due to the drilling process, and then we track actually those cuttings through the transport. Each time we change the flow rate and rotational speed of the drill string, so we see how those cuttings are being transported. If you were using like carrying transport index, so what you will get is an overall picture regardless of how much cuttings you are actually producing. So that will not help enough. So you really need to track the cuttings where they are and the life through the transport to be able to predict what is the cuttings flow rate out of the well, because this is delayed by several, well, not only minutes but hours before they get out of the well for long wells.
You've mentioned a few, quite a few transient effects, like cuttings, we just talked about again, thermal compressibility, retention in the pumps. And you also mentioned that we can model all of these. Can we model all of these in real time, or what sort of real time analysis could we gain?
Yes, this is possible to model in real time, but as any model, a model needs to be calibrated. So because the input are uncertain, there are a lot of uncertainties in both the metallurgical properties and the actual compressibility and many different parameters. So those models need to be calibrated, and the calibration is quite important there. When it comes to the modeling of what happens into the return channel, that needs to be calibrated through the first 3-4 stop and start of the mud pumps. That gives you enough information to calibrate the model, and afterward it is more or less stable for the rest of the section. When it comes to pressure losses and the impact of compressibility, that is very helpful to have PWD information to do the calibration, to separate the pressure loss into the drill string and the pressure loss into the annulus, as that has quite some impact actually on the amount of fluid that you will need to compress into the well to compensate for the pressure gradient. If you don't have the PWD information, this is less certain, because you can predict well actually the flow rate out of the well. But that is possible to do that in real. So calibration can be done automatically, and the model can run in real time. But all this depends on good quality description of the wellbore. So if you enter something which is not precise enough, then the calibration method will not converge very quickly, and we struggle a lot to try to find something which is making sense. So good quality data is, as usual with models, quite important.
Thank you. You talked a lot about compressibility. Is this to what extent is this dependent on the mud that is chosen?
It's quite dependent on the mud, and it's not only it's the compressibility and the thermal expansion, and that both aspects needs to be accounted for, because the mud, when it is inside the well, will be exposed to a large range of pressure and temperature, and that will change the density of the mud. and therefore there are relation between mass and volume. The compressibility and thermal expansion needs to be calculated for the composition of the mud that you have. So we need to account for the amount of solid which is there, both high gravity and low gravity solids. We need to account for the different type of fluids which is there. So if we have an oil-based mud, then you have a mix of oil and water. So we need to account for both of them, and we need to have a good description or knowledge about the compressibility of the base oil, because not all the base oil have the same PVT behavior. And when I say compressibility, I mean both compressibility and thermal expansion. And for the brine, it's more like linked to the salt content. So we need to know what kind of salt is there and the proportion of salt which is there, and then we can calculate the PVT behavior of the brine. So yes, you really need to know the oil-water ratio. You need to know the type of base fluid that you are using, and also the density of the fluid at a given pressure and temperature to basically get the amount of barite and possibly low gravity solid which is included into the fluid, as it will influence quite a lot this compressibility that you have, or the compressibility and thermal expansion that you have inside the well, because the density is, as I said, very variable inside the borehole, both inside the string and inside the anus, as they are subject to different temperature and pressure.
Another question from the audience: is it possible to use this modeling for biphasic fluids with N2?
Oh, this is more complicated. If you think about foam drilling, for example, that there will be a lot of compressibility due to the gas phase into the and that is much more complicated to predict how much the compressibility will be, and the impact of temperature on the thermal expansion. We've tried to apply that method for some as a post-analysis of an operation using foam, but that was a post-analysis, that was not real time, and we saw that there was a lot of uncertainties in every place. So even though the focus was not on gain loss detection, and that was more on cutting transport, we could get some information, but of course it's much more difficult to analyze. We've tried to apply that method for some
Thanks.
using foam.
Is there a way to distinguish direct mud treatment in the pits from abnormal pit volume variations?
Well, it's possible only if you have some source of flow rate out measurement out of the close to the outlet of the well. Because if you look at if you have a flow paddle or if you have a chorus flow meter, you can check whether this increase or decrease in the pit volume is related to is also detected by the flow meter device that you have close to the outlet of the well. Otherwise, it's rather difficult. So you may try to see if the pattern is very linear, which may indicate that you are pumping something into the pit, but that is not a guarantee either. So you need a second source to be able to detect that.
Have you got any other questions coming? Any? Or any thoughts? Any comments?
You asking me?
No, I'm guessing I'm asking the audience at the moment. Although if you've got some thoughts to add or comments, then of course feel free to.
No.
Have you got any other questions coming? Any? So we've discussed a few ways the work can head. Are you have you got any thoughts of which way you're going to head with the insights that you've gained, or are you still keeping everything open?
Yeah, no, I don't think we have solved the problem at all. I think we have scratched the surface of the problem. What I think is really would be very valuable is to have something which can measure the flow rate out of the well, which is having a small footprint and being reliable. That would be a good source of information. But that would help actually, because as we discussed, there may be a lot of things happening into the pit, and that is often the problem, which is making the gain loss detection difficult. So having something to measure the flow rate out of the well, which is reliable and small, so that it can be retrofitted in existing rig, would be very nice.
Okay, thanks.
Wonderful. Thank you so much. Sorry to interrupt.
I was just going to pass on to you.
Thank you, Andrea, and to Eric, and thanks to the audience for your participation today. And before you log off, if you can please just take a few moments to fill out the webinar evaluation. You can find that in the links box on the left side of your screen there. Just click on link number 2. As I said, it only takes a few moments to fill out. We would love your feedback. From the links box, you can also print off a copy of today's slides.
Wonderful. Thank you so
This
much.
program is copyright 2017 by Society of Petroleum.
Thank you, Andrea, and to Eric, and thanks to the audience for your participation today. And before you log off, if you can please just take a few moments to fill out the webinar evaluation. You can find that in the links box on the left side of your screen there. Just click on link number 2. As I said, it only takes a few moments to fill out. We would love your feedback. From the links box, you can also print off a copy of today's slides. This program is copyright 2017 by Society